Hi everybody, I'm Torul Başlı, and today I'm going to talk about the error made by Leibniz based on probability theory. So, in the second slide, let me give you a brief introduction about Leibniz. Leibniz was a German polemist and one of the most important logicians and mathematicians. Development of the differential calculus and integral is considered to be the major accomplishment of German scientists. And today's our main topic is related to the mistake that is done by Leibniz. And his little proposal was that in a single roll of pair of dice, it is equally to get the sum equal to 11, obtaining 12. Since he assumed that both events can be done only in a single action, probabilities of both events will be the same, more likely to be 1 divided 36. In the third slide, we have a question here. Why Leibniz failed to explain probability of mentioned events? In the next slide, I have an answer here. Leibniz didn't consider probability of events as a ratio of advantageous case to general case instead of taking it as a one of 11 cases possible. 11 here represents a number of some values. In the next slide, we have let's move the explanation of this phenomenon supposed by the Leibniz. As it seems from the table, it's always that there are two possible attainable cases in which the sum is equal to 1. I think this was a major point where Leibniz did a huge mistake by not considering the probability of getting sum 11 in two cases. However, at a glance to the case which involves a pair of 6 and 6, in both dice, we observe that sum becomes equal to 12 only and only when the number 6 appears on both dice. In the next slide, we have here, and taking a look at the probabilities of two events, in general, we see 36 possible cases where two of them is advantageous for us to get sum equal to 11. In that case, the probability of this event turns out to be the 2 divided to 36. But when we just take sum equal to 11 to 12 into account, it is only viable in the pair of 6 and 6, which makes the probability of the event to become 1 divided 36. The probability distribution is represented here as well. In this table, you can see the probability of each event which takes the sum as a basis for considering the number of possible causes. In the next slide, we have here, from another point of view, I will show another way of solving the present problem which involves rolling of one after another instead of throwing them at the same time. Here you see the probability distribution of each event while rolling of one die. And as you see here, each event predominated with the probability of 1 divided 6, since there are 6 events that occur in terms of appearing numbers on the die. And in the next slide, it's almost the end. Here we do a calculation like this. We have said that if we want to get sum equal to 11, we should consider the pair as 5, 6 and 6, 5, which contains the appearance of 5 in the first row and 6 in the second one, respectively. At the same time, we should take into account the vice versa. So we'll calculate as the probability of getting 5 firstly multiplied by the probability of getting 6 in a second dice, making 1 divided 36, and adding also the vice versa, which also equals to 1 divided 36. So in total, we get probability of sum of 11 to be identical with the previous one, 1 divided 18. For 11, it's almost crystal clear that even gets real only in the case when both of dice will have number 6 in the appearing phase. So the last slide